I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students and for my wife's cookies, Lord. In your name I pray. Amen. Okay, so first order of business, a short example. So I said say something about polar coordinates. So this is a kind of fun example. If we look at T is a mapping from, let's say, R2 to R2, defined as follows. T of r comma theta equals to r cosine theta, r sine theta. You might recognize this as the polar coordinate map, right? So if you were to calculate the Jacobian of T, the Jacobian of T would be a 2 by 2 matrix. It's partial T, partial r, partial T, partial theta, all right? And so you can calculate that pretty easily. It gives you cosine theta, sine theta for the first column, minus r sine theta for the second column, r cosine theta, like that. And so then if we want to use the linearization idea I was telling you guys about, we can linearize this change of coordinates as follows. We can say T of r, well, let's say T of a little change in r with a little change in theta, all right? It's actually going to be equal to the Jacobian of T times a little change in r times a little change in theta, which that works out to what? Times the change vector here. So if we work this out, what does it give us? This gives us that we got, let's see here, cosine theta, change in r, minus r sine theta, change in theta, comma, sine theta, change in r, plus r cosine theta, change in theta. Great. So if you call this, say, delta x, delta y, all right, thinking of the outputs of this being x and y, right? You could compare the area. You could compare the area of the delta x, delta y, right, versus the area of the other. What I'm trying to say is you could compare how much area, well, anyway, the area here with the delta x, delta y side is what? Delta x, delta y, right? What's the area of this? Well, it's actually, oh, I'm sorry, guys. I'm muddling this stupid thing. I'm not getting across the point. I didn't need to even write all this out. I'm so sorry. I had to erase. The larger point is that while the polar coordinate change formula is nonlinear, if we look at its derivative, right, that's the best linear approximation to the change in the function. And we can think about what does a linear transformation do to an area. What does a linear transformation do to the area before and after? Like if we start with a parallelogram, then we take T of the parallelogram, how is the area of the transformed parallelogram related, right? So if we look at area of P versus the area of the Jacobian of the transformation times P, if you'll allow me that language, well, this, of course, would just be the determinant. I mean, it's the determinant of whatever, vectors span the parallelogram, right? Let's say V1 and V2 for the sake of discussion. What's the area of this? Well, this is the determinant. I mean, and so I guess we should just say, I'm sorry, guys. I'm missing something here to say to you, and I'm just struggling. So the point is that the determinant of J is what? we got our cosine squared theta plus our sine squared theta, which is r. So what I'm trying to get across here is that this is why we can rewrite delta x delta y as r times delta r delta theta. You can really just think about that as being a consequence of the fact that the Jacobian matrix, the determinant of that Jacobian is r. Now you see this in calculus 3 without the matrix stuff, right? We just say, oh, the Jacobian, but the Jacobian's already a determinant. What you're doing is you're taking the determinant of the coordinate change matrix, well, the derivative of the coordinate change, actually, which is the best approximation to the change of the function at a change in the mapping at a point, which is really all you need to describe differentials and how they're related. So I'm sorry, I'm not doing it justice. This is something I try to explain better in advanced when I teach it. I'm going to go on. 2. And so this will be neater. Sorry, this is a little bit vague. My apologies. I want to study, if we want to solve dr dt equals to ar, oh, and I get tired of this notation, so I'm just going to say dx dt equals to ax, all right, where A is n by n matrix, all right, over the reals. So what we're looking at here is a sneaky notation, a really elegant notation for n first-order differential equations in n unknowns. So just to demystify it for a second here, if I can find my markers. Found them. Woohoo. So here would be a very silly example of this. Let's start out with something nice and silly. dx dt equals to 3x, dy dt equals to minus 2y. Now you learn how to solve these kinds of differential equations in calculus 2, right? This implies that dx over x is equal to 3 dt. The bottom one implies that dy over y is equal to minus 2 dt. You integrate both sides, you do a little algebra, and what do you find? You find that x is like c1 e to the 3t. You find out that y is c2 e to the minus 2t. There you go. So we solved this system of differential equations using calculus 2, separation of variables on each one at a time. Yay. All right. So what's the point? Why do we need a matrix? Well, for this one we don't, right? But as a matrix, this problem looks like the following. It looks like dr dt equals to 3, 0, 0, minus 2, xy. What is it?
The second integral should just be 2.
Oh yeah, I made up an extra t. Sorry about that. That would be something different. My apologies. So, you know, here's the struggle. I want to use x here, but I want to use x here. It's like, but I can't do both, right? So, fine. Try to keep me out of trouble. I'll use r vector in places. See, how do we solve that? Okay. Well, this, like I said, this one we can solve. But what about when the differential equations are more sort of tangled, right? So what if you had something like dx dt equal to x plus y minus z, and dy dt equals to x plus z, and dz dt equal to, I don't know, 2y minus 3z, something like that, right? Then these are coupled, right? In other words, the differential equation for x depends on the variables x, y, and z. The differential equation for y depends on the other variables. See, so the strategy I used in example 1 no longer works, does it? Right. Example 2, we're stuck. We cannot just do calculus 2 piece by piece, right? So that's why the theory I'm about to share with you is so beautiful and kind of shocking. Definition. E to the TA is equal to the sum n equals 0 to infinity of t to the n over n factorial times a to the n. Of course, you could just write that ta to the n over n factorial. This is the matrix exponential. It's a matrix-valued function of time. You could also call this exponential of TA if you like that. And so here, exp is a mapping from the reals to Rn by n. Okay? You're like, well, that's an infinite series. I learned in calculus 2 that infinite series can converge or diverge, right? So in more detail here, e to the TA, here's the details. The identity matrix plus t times a plus 1/2 t squared a squared, 1 over 3 factorial, t cubed, a cubed, and you get the story. So the story goes, this is the matrix exponential. Well, if you look at my chapter on differential equations, you'll see in there I've given you, I think I have the proof in there that this series converges for any matrix. Now, there's a separate proof that the matrix converges. Something I haven't emphasized enough for you guys is that, we found this Jordan form, right? What's the point of that? Well, if I have a real matrix, I can find the real Jordan form, right? If all the eigenvalues are real, I can find the Jordan form. In your homework, I show you that if you have the Jordan form, you can calculate the matrix exponential. Like the lambda piece gives you a diagonal matrix with lambdas. The blocks, if there's ones in it, that gives you this other e to the n piece, which is a finite. It actually finitely truncates. It's not actually an honest-to-goodness infinite series. It truncates a finite order. The point is, if you study carefully the real Jordan form or the Jordan form, you can calculate the matrix exponential of a real Jordan form or a Jordan form. It's not that hard. But we also have the theory that any matrix is similar to a Jordan form or a real Jordan form. And not just that, in your homework, you prove that you have an identity. In particular, you prove this. P inverse e to the b p is equal to e to the p inverse bp. So if you take b equals to t times a, well then that basically shows you that if you can calculate the matrix exponential for Jordan form, which I essentially trace out in the homework, at least in the real case, for the real Jordan form is not much different. I may not have put that on you in the homework, yeah? But rest assured you could do it. Well, that means we can calculate e to the TA for any a because there exists the real Jordan form for every possible matrix. So setting aside whether or not you can follow the analysis in the differential equations chapter, that's a concrete calculational argument that you can calculate the matrix exponential for any matrix. You just have to find the Jordan form and follow that formula. All right? Which is kind of neat. You say, well, that's great, but what does this have to do with differential equations? Right? Because I just kind of jumped topics. It seems like I jumped topics, doesn't it? What happens when we differentiate the matrix exponential, ddt of e to the ta? What happens there? Well, so, by the way, how do you take the derivative of a matrix-valued function of time? You do it component-wise. So long story short, if you just do calculus on matrix-valued functions of time formally, it works out. Everything is what you'd think it would be, for the most part. For example, the derivative with respect to t of ta is just a. What's the derivative of the identity matrix? It's 0 because it's a constant matrix, so that's 0. So we get a. What's the derivative of 1/2 t squared a squared? Well, a is constant, right? So a squared pulls out, and you just differentiate 1/2 t squared, which gives you t. So we get a plus ta. And then the 3 cancels with 3 factorial, leave me 2 factorial. 1 over 2 t squared a cubed. There was a square there, wasn't it? Sorry, guys. A squared, that's what you guys talk about. A squared, A cubed. What's next in the story here? If one more thing I didn't write, but 1 over 3 factorial, t cubed, a to the 4th. Well, if you just tilt your head and squint, you can see that that's a times I plus ta plus 1/2 t squared a squared, and so forth. Or you could factor a out on the other. I mean, you got your choices. You can factor a out to the left or to the right, whatever floats your boat. But anyway, I'm going to do it this way. That's a e to the ta. Whoa, that's kind of cool. So a matrix exponential differentiates just like an ordinary exponential, right? The derivative of like e to the 3t is 3e to the 3t. Exponentials are very forgiving. You know that? ddt of e to the 3t is 3e to the 3t. ddt of e to the 3it is 3i e to the 3it. And now this. Like the matrix, the notion of exponential, calculus on the exponential is very forgiving to those who are mathematically ignorant. If you have a fuzzy notion of calculus with that exponential, you're probably still going to be right, even if you don't understand a bit of what you're doing. Right? Certainly a person could do this calculation without understanding anything that we just did. Maybe you're that person right now, and that's fine. I'm just kidding. Okay, so the larger point here is that e to the ta, you could look at as, say, x1 vector, x2 vector, xn vector, right? It's actually it's a matrix of functions. So when we differentiate a matrix of functions, what's that look like? How does that work? Well, it works component-wise, but that also means it works column-wise. In other words, the derivative of a matrix of functions is the matrix of derivatives of the columns of said functions, like this. That's how it works. So if you look at what we just proved, right, what's this ddt of e to the ta mean? We had d to t, e to the ta equals a e to the ta, right? So I'm saying that that's a times, x1, xn. Remember the column by column multiplication? So we can rewrite that as ax1, axn, like so. But on the other side, right, we've got that's equal to what, column by column? The derivative of x1, right? This is also equal. So let's compare these two column by column expressions. What did we learn? What did we learn as we compare those? Comparing this with this, what did we just find? We found that dx sub j dt is equal to a x sub j for all j, ranging from 1 to n. What does that mean? What does that say about the column of the matrix exponential, any column? What does it mean to be a solution to a system of differential equations, right? Go back to the starting point, right? This guy. What's the solution? Solution is something like r equals to x sub j, where it works. In other words, if I plug in that function, that column of functions, vector of functions, when I differentiate it, it's the same as if I take the matrix A and multiply. So what I've just proved for you is that every column in the matrix exponential is a solution to the differential equation dx dt equals to ax. Right? Each column in e to the ta solves dr dt equals to ar. Now, here's the theory of linear differential equations in a nutshell. Theorem. The general solution to dx dt equals to ax has form x equals to c1 x1 plus cn xn, where x1, xn are linearly independent solutions to dx dt. Now, what do we mean by linearly independent solutions? You guys know what linearly independent solutions means. That's not mysterious. What I mean by linear independence of solutions is exactly what we usually mean. That means that c1 x1 plus c2 x2, right? Cn xn equals 2. 0 implies what? C1 all the way through Cn is 0. But you got to recognize something here. This is not just a linear combination of static column vectors. This is a linear combination of vectors of functions. So this is actually a function equation. This is understood to be for all t in the reals. If I was to write down, you know, we could write, this is really of t, of t, of t, right? So what does that mean? You could rewrite that as, what you need is that x1 dot xn, if you look at that as a matrix of functions, that times c1 through cn is equal to 0, has only the what? Yeah, only the 0 solution for all t. Again, this is at time t. Now we know if we have a matrix and we want it to have only the 0 solution, we want it to be invertible, right? Now, below the dotted line, I was trying to use x1 through xn as if they're arbitrary, okay? Above the dotted line, the x1 through xn were specifically the columns of the matrix exponential. I made a change in focus below and above that dotted line, okay? But actually, that's not bad notation, because in fact, the columns for the matrix exponential can be taken to be like that x1 through xn, which are linearly independent. Why? So can you guys tell me what the inverse for the matrix exponential is? What's that? Natural log? No. Easier than that. Not that kind of inverse. Here we're talking about matrix multiplication, not composition of functions, but yeah. How about this? If I want e to the 3t times something equals to 1, what do I put here? E to the minus 3t, right? Yeah. You know what? Yes, indeed. E to the minus ta is the inverse. You can prove that. You can multiply the series for that with the series the other one, and you get this beautiful truncation, and all you're left with is the identity matrix. That proves that the columns are linearly independent and hence form the general solution set. Long story short, if we want to solve dr dt equals to ar, then r equals to some e to the ta times, well, times r naught. There you go. That's a solution to the initial value problem. At time 0, it gives you r equals to r naught. Because what's e to the 0? It's the identity matrix. So e to the 0 times r naught is just r naught again. There you go. That is the solution to the initial value problem for n equations and unknowns for arbitrary coefficients. And you know how to calculate that if you follow the homework, because you can do similarity transformation. Now I teach a different method in differential equations in terms of multiplying by eigenvectors and generalized eigenvectors. And in truth, that's better. But you know what? This is not a differential equation, so I'm not going to teach that in here. We have a method. You can just calculate the Jordan form, do similarity transformation, bam, you solved it. So this is yet another use of the Jordan form, is we can solve pretty much any system of n differential equations and n unknowns. Not pretty much any. I don't need to water that down. But there's more. Now, the neat thing is, guys, the thing I just talked about, that the inverse, you know, that the inverse of the matrix exponential is just minus the argument. That's part of a larger story, which I think is interesting in its own right, and I should share just a word or two with you about. There's a formula, e to the t a. The determinant of this, actually, is equal to the exponential of the trace of ta. Well, let's forget about the t for a while. Let's just say that the determinant of e to the a is the trace, exponential of the trace of a. This identity is pretty easy to prove if a is in Jordan form. So, you know, well, I'll just say that. You can prove this. If you put a into Jordan form, it's pretty easy to verify this identity. If a is diagonal, it's even easier. Suppose a is diagonal for a second, right? Then what's e to the a? It ends up being e to the lambda 1, e to the lambda n. I would get into details, but I think I'd be doing your homework. There's really, it's not hard to prove this. You don't have to be fussy about the analysis in here, okay, guys? I'm not expecting you to be careful with convergence arguments and so forth. But anyway, that's that. So what's the determinant of this? Product of the diagonals, right? Which is what? But on the other hand, what's the trace of a? Right? So this is nothing more than e to the trace of a. And I'm sorry, I use the exponential notation both for the matrix exponential and for the ordinary exponential. And it's bad on my part. Some people make a technical distinction between these. I am not such a person, sorry. But there you go. And this is true not just for a diagonal matrix. You can run through the same argument for the Jordan form. It's not much different. It's obvious that the trace of a Jordan form is still just the sum of the eigenvalues on it, right? Because the Jordan form is super diagonal. What is on the diagonal is just the eigenvalues, right? And also, well, anyway, this is not much different for Jordan form. So this is one thing. And so what does this tell us, by the way? What does it say about e to the a? Well, I guess we already knew this. E to the a is what? Invertible, right? But you can even see it more explicitly from here, right? Because e to the trace of a is what? That's an element of the real numbers going from 0 to infinity, right? For real matrix. So what you can do, it's kind of interesting, is you can look at paths in the group. how much. Okay, we got just enough time for me to get into trouble. So if we have, well, more generally, there's a story I can tell, which is that there's a Lie algebra. And over here, there's what's called a Lie group. And if these are matrix, both matrix, there's a more abstract notion of these things, but the matrix exponential takes you from one to the other. For example, we can talk about GLN, and then you get G big LN. You can talk about the special linear Lie algebra, and that maps to SLN. You can talk about the orthogonal algebra, and that maps to ON. So the basic story is that you use the lowercase letters for the Lie algebra, the uppercase letters for the Lie group. And what I said is a lie. The exponential doesn't get you to everything. In fact, the exponential just hits the connected component of the identity. For example, GLN has two different kinds of matrices in it. It's got positive determinant matrices, and it's got negative determinant matrices. So the exponential is never going to hit one of the negative exponent, one of the negative determinant matrices, because the matrix exponential has positive determinant. So, just to give you a brief window inside this world, if you had, for example, this is going to be a little bit abstract, but suppose this is a picture of your orthogonal n by n matrices over the reals, right? In there, you've got the identity matrix, right? And you can think about taking a curve of matrices that goes through the identity matrix like that. And so the formula for that would be something like gamma of t equals to e to the, well, let's say tb. And the thing is, if this is an element of ONR, then that means that this satisfies a formula. What formula do we have to satisfy to be in ONR? Well, we have to satisfy gamma transpose gamma equals to the identity matrix. That's the orthogonal matrix condition, right? So if it's going to be a path, a curve of orthogonal matrices that goes through identity, it has to satisfy this equation, and of course, we know that gamma of 0 is equal to the identity by assumption. Well, you can prove that is actually realized as the exponential of a matrix B. And so like this, if we differentiate this, we get d gamma transpose dt gamma plus gamma transpose d gamma dt equals to 0. And what this shows me, by the way, if, setting, well, if we plug in times 0, what's that give us? It gives us d gamma dt transpose plus d gamma dt is equal to 0. Therefore, d gamma dt transpose is equal to minus d gamma dt at time 0. But through arguments I'm not really showing you, you also have that gamma of t is this, right? So what's d gamma dt? It's also b e to the tb, right? So gamma prime of 0 is just b. And so what we find by this little calculation is that the curve of matrices which goes through the identity that arises as the exponentiation of b, well, that b, it's not just any old matrix. This b has to actually satisfy a certain condition. In particular, b transpose has to equal to minus b. And so what this calculation is actually showing us is that the Lie algebra of the orthogonal matrices is the antisymmetric matrices. In other words, if you exponentiate an antisymmetric matrix, you get an orthogonal matrix. This is the interplay between Lie algebras and Lie groups, both of which are throughout modern physics. But at the base of it all, you know what? It's just matrix calculus, which is built over the things you've done in the semester, and their synthesis with abstract analysis, which is one of the next chapters that you could read in your mathematical development. But maybe not right away. Maybe after abstract algebra, it's a better idea. I don't know. I should misbehave every once in a while in this course, so this is now. I give you cookies, right? I'm allowed. So, I don't think this particularly helps you with the homework. My apologies. I should tell you, before I forget, it's still on, right? Okay. Problem, what was it? 154, the one that has the E1, E2, E3. I should have said that those are distinct and positive. Or, well, distinct and non-zero. They don't have to be positive, but I do not want the eigenvalues to be 0. If the eigenvalues are 0, the thing I say about the column space and the null space is no longer true. You could see that from studying the eigenvalue 0 problem I did on the board. If you have any other questions, if you're worried that, like, you know, problem's missing an assumption or something, just let me know. Or just add it and solve it with the added hypothesis. It's probably work out. Sorry you don't have a lot of time for this one, but, you know, when's the test? Friday, yeah, so. What would you guys most need to hear more about Wednesday? What would be most helpful? If I had to focus the review on something, where would it be that you need to hear the most about? Is it eigenvalues? Is it orthogonal? Everybody good on Graham-Schmidt? What's what? The Jordan form. So analyzing Jordan form? Okay, we can focus on that. Thanks, guys.